For decades, people thought that the heaviest atoms, including elements like lead, gold, uranium, and plutonium, were formed in supernovae. Modern nuclear theory suggests that the nuclei heavier than iron form when lighter elements rapidly absorb neutrons in a process called rapid neutron capture. Typically, adding neutrons to a stable nucleus forms unstable isotopes, leading to radioactive decay. But in neutron-rich conditions, atoms can quickly absorb neutrons in succession without decaying, forming heavy unstable atoms, which eventually decay to form the heavy elements. Previously, supernovae explosions were thought to be powerful enough to provide the neutron-rich conditions needed for the LAUR process. But recent observational data and simulations using high-performance computing suggest that collapsing supernovae do not provide the high entropy and neutron-rich conditions for nuclear synthesis. So what objects in the universe could supply the neutron-rich conditions needed for the LAUR process? Neutron stars, the remains of supernova explosions, may be a viable option. They're some of the densest feasible objects in the universe, made up of neutrons weighing 3 solar masses, housed in a core the size of a small city. In 1974, Latimer and Schramm proposed a theory that violent disruption of a neutron star by a black hole or neutron star merger might be strong enough to unbind the neutron-rich material needed for the LAUR process. During a merger, neutron-rich matter, with 1% of a solar mass, is ejected at a fraction of the speed of light, furnishing ideal conditions for LAUR process nucleosynthesis. In a groundbreaking discovery in 2017, the LIGO Virgo Observatory simultaneously detected gravitational waves and a glow of light coined a kilonova, which comes from the decay of synthesized LAUR process elements. The timing of these two events suggests that these two signals were the afterglow from a neutron star merger, located 130 million light-years away. The kilonova detection opened up a new world of opportunities for studying the origin of heavy elements in the universe. Up to the task, a team at Los Alamos National Laboratory, led by Chris Fryer, used state-of-the-art codes to construct a pipeline of realistic models of the kilonova, spanning expertise from multiple areas in astrophysics, nuclear, and atomic physics. These models cover various aspects of the LAUR process scenario. After the initial collision, ejecta evolves quickly on a timescale of a fraction of a second, reaching about 10,000 kilometers across and a temperature of more than 1 billion degrees. Neutron-rich matter expands in the plane of the merger, forming pockets of high-energy outflows in the center plane with extremely high heating rates and internal energy. This is when the rapid neutron capture process is operating. At later times, the expansion becomes homologous, with higher electron fraction material near the polar regions. This model needs to be expanded by Fleck SPH code, which expands the model from its original size of around 3,000 kilometers to the kilonova scale, which is the size of a solar system. Simulated ejecta from the accretion disk provides temperature and density data for nucleosynthesis codes like PRISM, SkyNet, and WinNet, which allow us to accurately calculate ejecta composition and the radioactive heating rate. Ejecta composition is then used to calculate detailed opacities for the radiative transfer code SuperNu that provides the final spectra and light curves of the kilonova. Spectral colors depend on orientation with respect to the observer, and the features which emerge may be used to identify specific elements in the composition like strontium and neodymium, which are expected to strongly influence the light spectra. From these simulations, we see that the non-uniform distribution of neutron richness in the ejecta leads to formation of complex structure in the expanding material. Thus, determining precision estimates of ejecta morphology to match with observational data from light and gravitational waves is a pioneering next step for understanding the amount that neutron star mergers contribute to our universe's heavy elements.